Hello and welcome. Let's talk about rationalizing denominators. So get yourself some lined notebook paper and a pencil because every time you're thinking, you should be writing. Those two should go together. And let me share my desktop with you. Okay, you should be seeing 3 squared is 9. You should know your squares. An exponent just means repeated multiplication. This means 3 times 3. So then what if I said 4 squared, you know that that's 16, 5 squared, that's 25, and so forth. But now what does a radical do? A radical or a root goes backwards. So the square root of 9, you should know that then would be 3. Okay? And if I did the square root of 16, you know that that's 4. The square root of 25, you know that that's equal to 5. The question a radical is asking you is, what's the base? So this is saying, what's the base that when I square it gives me 9? The base is 3. So it's going backwards from the exponent. It's giving you the base as the answer. And in fact, you could think about it like this. You can think about the square root of 9 as equal to the square root of 3 squared, right? And so the square root of 16 is equal to the square root of 4 squared. And the square root of 25 is equal to the square root of 5 squared. And so we have this general principle that says if I have the square root of x, just some number, squared, it's equal just to x. Because there's something that goes right here in a radical. That would be the index. And when it's not written, the index is 2. And so when the index matches the exponent, they kind of cancel each other out, and you just get the base back. So this would be the square root of 3 squared. And these then, if they match, they cancel. I just get 3. The square root of 4 squared. These match, they cancel. I just get 4. And so forth and so on. But we can also do that with cubes. So those were the squares. Now let's do something like this. What about 2 cubed? That's 8. Reverse the process. What is the cube root of 8? That's equal to 2. Because really it's the cube root of 2 cubed, right? Do you see how when I do them as an exponent, you see that the index and the exponent, if they match, they cancel themselves out? Same thing here. What if I said 3 cubed? No, let's not do 3. 3 is like, it's a duplicate number. Let's do 4 cubed. That's going to be 64. So what is the cube root then of 64? Well, that's equal to the cube root of 4 cubed. 4. When the index and the exponent match, you just get the plain old base out. All right? Now, let's talk about rationalizing a denominator. When you have a fraction, it means division. And so let's say I had 3 divided by the square root of 5 down here. It's easy to divide by 5. It's not very easy to divide by the square root of 5. So the question is, how do I change this so that I've got an integer or a whole number or at least a rational number in the denominator? Well, remember that I can multiply something through by 1 and not change the value, right? If I multiply 3 over the square root of 5 by 1, I don't change what the value is, but that's not very effective. So let's make it a fraction. If I multiply the top and bottom by, I don't know, 4 over 4, isn't the value of that fraction still 1? And I would get 12 over something 4 times the square root of 5. But that's still not very effective, but we're making some progress. What if I multiplied it by something that would cancel the denominator root? It would get rid of the square root in the denominator. How about the square root of another 5 on the bottom? And then, of course, I have to multiply by the square root of 5 on the top because the overall value of that fraction has to be 1. Now watch what happens. The numerator is not all that interesting. 3 times the square root of 5. they can't be combined to be 15 because it's not 5, it's the square root of 5. But the denominator now becomes this. If I've got an index that is the same, a square root here and a square root there, and I multiply them, I can multiply the radicands together, the things underneath the square root. So this is really the square root of 25, which is 3 root 5 over 5. This is now exactly equal in value to the original right here, but it has an integer or a rational number in the denominator. Another way to think about this is for this step right here, you can think about it like this. It's 3 times the square root of 5 divided by the square root of 5 squared. And look, the indexes match, right? So when the indexes match, the radical cancels, and I just get out my denominator with the base, 5. Okay? So now let's talk about this one. What if it's a cube root in the denominator? So it's 3 divided by the cube root of 2. Well, again, I'm going to multiply it by something that's going to cancel the radical in the denominator. What I need is I need the cube root of something, because the indexes have to match in order for you to multiply them together. So it's going to be the cube root of that same thing on top. But look what I've got down here. I've got 2 to the first exponent. I've only got one base of 2. How many do I need in order to simplify it out? I need 3 of them total. See, the index tells you how many you need total to simplify. If I've got 1 and I need 3 more, or not 3 more, I need 3 total, how many more do I need? I need 2 more. So it's 2 squared. Because what I'm going to do is I'm going to combine these. 2 2's here, 1 2 here. Gives me how many 2's then in the end when I multiply across. I hope you can see that it gives you 3. That kind of rhymed. So on the bottom now, which is what I'm interested in, the cube root of 2 cubed. Ta-da! Top, I really don't care. 3 times the cube root of 4. That's really not all that relevant. Do the indexes match the exponent? This matches that? Good. 2. And then the top just stays 3 times the cube root of 4. There we go. I have now rationalized that denominator. Whew. So you've got to get the same number of bases under the radical sign that you have as the index so that they will cancel themselves out. Anyway, may your day be merry and bright, and may all your mathematics be right.